Good morning, good afternoon, and good evening, whenever you're watching this. Today we'll be discussing hydrogen chloride and deuterium chloride, and really trying to understand what really is the difference. My name is Precious Nwankwo, and this experiment was conducted by Chagwo Wang and I. In order to understand this difference, we're going to be using infrared spectroscopy. I'm sure you're asking, what is infrared spectroscopy? What is IR? And if you're not, get ready to see you. Well, IR spectroscopy, also known as infrared spectroscopy or the other way around, can be used to fully understand the structure and the presence of small molecules in the gas mixture, in the liquid mixture, and it can be used in many other forms. Although in this case, we're going to be using it in the gas mixture to understand the vibrational and rotational motion and to see the energetic differences in diatomic molecules such as HCl and DCl that we were trying to figure out. We're going to be testing the vibrational and rotational motion and the energy quantization and the influence of molecular rotation on vibrational energy levels and the other way around. So what do we want to know? What do we want to know the difference between? So based on the information that we already know about HCl and DCl, which is that DCl is a form of hydrogen chloride, although it has more neutrons, it is hypothesized that the vibrational constant, which is determined by K, will be the same for both HCl and DCl because they have similar electrostatic bonds. And deuterium's extra neutrons will not affect the properties of hydrogen and deuterium and the deuterium chlorine bond. So what do we do in order to figure this out? How did we set this up? So in order to facilitate this experiment, this chemical reaction using D2SO4 and potassium chloride was done in order to get HCl and DCl into our IR gas cell. So this right here is our IR gas cell. This is our whole reaction apparatus. Our D2SO4 was put into our syringe here. Our potassium chloride was put into our round bottom flask in the solid form. The D2SO4 was then added dropwise into our KCl, excuse me. And inside this round bottom flask, once the experiment is up and going, we'll be creating K2SO4 solid here. Although what we actually want is the DCl gas that will be created, and that DCl gas will then travel through this apparatus into our IR gas cell. This is all done under air-free conditions, so we want to make sure that this is all oxygen-free before we even start. And once that is done, once we know that we have our DCl gas into our IR gas cell, we'll remove this needle to then trap the IR gas cell and clamp it here, which we can then remove and transfer to our instrument. The IR instrument we're going to be using is the Perkin-Elmer Spectrum 2. The this instrument was already calibrated before we took our IR gas cell with the DCl2 over there. So the software has already been up and running and calibrated. We're going to put our IR gas cell into the instrument, open up our software, and we're going to set up a certain set of parameters, which is including a wave number range of 1,000 inverse centimeters to 6,000 inverse centimeters. So what does the data look like? This graph here on the left, or this spectrum here on the left, is produced by the Perkin-Elmer Spectrum 2 software. And these two sets of peaks here, or ranges of peaks here, are going to be our R branch and our P branch. Our R branch and our P branch represent the two transitions and the two different types of energy levels transitions based on, and the peak and these blue labels on top of the peaks here are the wave numbers at which these energy transitions happen at. So based on the P branch here, this energy transition here is corresponding with this one here for the energy transition from 1 to 0, and the next peak is from 2 to 1, and the next peak is from 3 to 2, and on and so forth for the rest of these transitions. And you can see it is also the same thing for the R branch, where a certain number of transitions have a corresponding corresponding wave number at which that peak is occurring at. This is our DCl fundamental, where we're going to go about it the same way. We're going to use our R branch or our P branch and just label them using the wave number at which the peaks are occurring at to understand the transitions to understand where these transitions are happening. And I'm sure you're looking at, okay, just putting them into a sheet, what can we really use with them? And you'll see that later the numbers will eventually be used to create a graph, and these graphs will then be fit to a line of best fit using a third order polynomial. And that third order polynomial will then allow us to analyze the data to get certain vibrational constants that we can use in order to understand the differences between the two. And the vibrational constant that we're looking out for is the force/spring constant that I was speaking about earlier, that is derived by K. We also have two more spectra, which is including the HCl overtone spectra, which is going to go about it the same way. We have our wave number corresponding to each transition, corresponding to where those peaks are happening in each branch on the spectrum. There's R branch or P branch. And this is our DCl overtone, which is going to be our last spectra, corresponding the same way. We're just going to label them, understanding the wave numbers at which these peaks are happening, which correspond to the certain level of certain transitions that are going on. So as I was speaking about earlier, we're going to eventually take the numbers that we got from the transitions and the wave numbers that we got and plug them into a graph, which will eventually get our third order polynomial. Our third order polynomials are going to reflect these polynomials here. This set of polynomials, this is for our P branch, which we're going to be used to analyze the P branch, the spectrums of the P branch and the graphs in the P branch and the third order polynomials that we get from setting up that P branch graph. And this is going to be for the R branch, whether it's for fundamental or overtone, it's going to go about the same way for the two of them. These can then be used to solve for the different set of variables that we have, which is going to be our VEXE, our VE, our V overtone, and our V fundamental. Sorry, our V fundamental and our V overtone, which could then be solved for our DE, which is going to be our DE and our D naught, which can be all used for using our V. So then using that V that we eventually solve for, we can then plug it into this equation here, which is going to give us our K. And this is what we really care about. Using the reduced mass of the DCl and the HCl, we can get our K value using 2 and pi and rearranging this equation with our V, which is one of the vibrational constants that we're going to solve for using the analyzation of the polynomials. We can solve for our K and then compare the two. Excuse me. So what do we do with the data? This is exactly what I was saying about. These are our third order polynomials that I was talking about earlier. And as you can see, we have them for the P branch and the R branch. And with that, we can use them using the equations I showed you in the slide before. We can use them to solve for all of these vibrational constants. Although the one that we really care about is this K value here at the bottom, which is 3.36 e to the positive 8 for both the P and the R branch for our HCl fundamental. This is our HCl overtone. And as you can see, it's going about the same way, although we're not actually using the overtones to solve for K. That is just applicable to the fundamental for the HCl and the DCl. As I was saying, here's our DCl fundamental graph. And here is the polynomials that we have here. These are the polynomials for the P branch and the R branch. And as you can see, we can use them to solve for the K value, which is the spring of force constant that we really care about. For this, it is 3.627 e to the positive 8 for both the P and the R branch. And this is for our DCl overtone spectra. We have our polynomials and we have the vibrational constants that we use to solve for them. So what does this mean? Overall, the hypothesis that we went about was valid. So based on the IR spectrum branches and the analyzation of the data collected, the spring constant K, or the force constant K that we were talking about earlier, remained constant between HCl and DCl in the fundamental spectrum. There's very little difference between them. With this data, it's confirmed that the basis of electrostatic bonds diminish the effect of the opposite charges in the atoms that would happen because of electron transfer. And of course, we're basing this off of that DCl has more neutrons, and we're trying to see, will the additive neutrons actually affect the force of the vibrational of the electron transfer, then the vibrational of the vibrational changes. And as you can see, for the force constant for the HCl is the same 3.36 to e to the positive 8 kilograms per second squared. And it's going to be the same it's going to be slightly different, but very much similar for the DCl, which is 3.63 e to the positive 8 kilograms per second squared also. So how can this overall experiment be improved? So throughout this experiment is emphasized not only for safety, but for capture of the product. We want to make sure that we get as much of that DCl gas into our IR gas cell as possible so that we get a really good readout. And this reaction must be done under air-free conditions because we want to make sure that it's only the DCl gas that is in our IR cell. And that's going to be difficult to always maintain, to make and to always maintain. So make sure we're setting up an air-free system that is up to standard. It's very important in this case to make sure that the experiment is done up to par and that it is done in a way that the results are usable and attainable. So why does this matter? Overall, why does IR matter? What can it be used for? Well, IR is very important because it is used prominently in the chemical industry and many other realms. For example, IR is being used at the moment to understand the vibrational features of glycosaminoglycan, structures in biomechanical and biomedical fields. And there are many other forms of IR spectroscopy. Understanding the fundamental uses and the fundamental ways to take and analyze the data that can be used, that can be received from IR, is a very important skill and can be used in many other fields. So as you can see in the picture in the bottom right corner, we have the GAG structure, or the glycosaminoglycans. They have a predicted structure based on the cryogenic IR spectroscopy that they received. And as you can see, that's what they're using now. Excuse me. Well, that's all I have for you today. Thank you all for joining. Hope you have a good one.